Swayam Prabha. Digital India. Educated India.
In this lecture, we will discuss about molecular dynamics of hard sphere systems. So, molecular dynamics method or the algorithm depends on whether we talk about soft potential or hard particle potential. For example, if you consider Lennard-Jones potential or soft repulsive potentials like this, where the potential energy smoothly varies as a function of the interparticle distance, we call these soft potentials. And all the algorithms we have discussed so far about finite difference method applies to these kind of soft potentials. And if you recollect the way we advance positions and momenta of the particles in the system, for instance, if you look at the Verlet algorithm, where the particle position is updated using the current position and then the position at the previous time step and then plus and then we have this acceleration. So, this acceleration is obtained from Newton's law, and this force is nothing but the gradient of the potential energy. And if the potential energy is a smooth function of r, then it is possible to get a differential form of the potential, and then you can do this MD simulation of soft sphere model, where we take time and then update time with some small delta t and then update the particle position based on the estimate of forces, and then both time, positions, velocities are updated in time, and we call this method as a time driven method because we take small time delta t and then at each of those time step we update the particle positions, etc. So, this is known as a time driven step by step method. Now, there are other kinds of potential we have discussed which are known as hard potentials. So, this particular model here is a hard sphere model, and the characteristic of this particular model is quite different from the soft sphere model because you can see this potential energy is discontinuous at r equal to sigma, because for r greater than sigma the potential is 0, at r equal to sigma or less than sigma it goes to infinity. Similarly, if you look at square well or square shoulder potential, also you have this kind of a discontinuity where one cannot calculate this differential form at these discontinuous positions. And you can also see in this kind of hard sphere particles, the forces are felt only during pairwise collision of particles. Between those collisions, the particles are moving at a constant speed or constant velocity. So, and during those interparticle collisions or before or after the interparticle collisions, you see that the particles are actually moving at a constant velocities. And during those particular flights, there is no force acting on it. So, we have to think about doing this MD simulation of hard spheres little differently from what we have done for soft sphere model. And the way we construct the algorithm for hard sphere system is that instead of looking at time and advancing time, here rather we conduct collision events and then update particle positions and other variables at every collisions. So, in a system of n particle, we basically find who is the next colliding partners, and then when they collide, we have to conserve energy and momenta, and then between those collisions all the particle will move there with respect to their velocities at a constant value. So, because of this, the hard sphere MD simulation is known as event driven or collision driven method. So, we are going to discuss in detail how to execute MD simulation of hard sphere systems. So, this is a general scheme when we try to think about doing hard sphere simulation of hard sphere MD simulations. First is we have to go to all the partners in the system. When you have n number of particles, then basically you have order of n square number of pairs, and then for each of those pair we can find what is the time at which these particles will collide, and then you can sort out collision times for each of these pairs. Some will have very long time because they may be going different direction, some of them may be very close to each other, moving towards each other, and because of that the collision time will be very small. So, you basically sort the values of collision times between different pairs in the entire system. Then we identify the next particle in the, so basically you find out which are the pairs which are going to collide next. That means whichever pair has the least amount of colliding time, you take those two pairs, and then we update particle positions until the collision occurs, and then we apply the collision dynamics for the colliding partners. This means ensuring that conservation of energy and momentum, and then you can calculate certain properties, for example, radial distribution function or any other property of the system. If you want to measure, you can measure in that particular time, and then you update the next collision partner. Okay, so and time can also advance, because we know that every time we make a jump of the collision time of the least value, and we will see all these things in detail. So now we are going to take just a pair of particle I and j, and then we look at what is the condition under which they will undergo collision or not. So we have two spheres, hard spheres I and j, and they have equal diameter sigma. This method can be also generalized for unequally sized colloidal hard spheres also, but for this particular example we take all the particle of a same radius or diameter, and then at some point of time t, let us say the position of I and j are given as Ri and Rj, and the respective velocities are given as Vi and Vj. Now, if these particles I and j were to collide at some future time t plus Tij, so this Tij here is what is I call the collision time of pair I and j. So we have the information at time t, and then now we are looking at the future at some point of time t plus Tij. If the distance between I and j is equal to sigma, okay, so that means at time t the particle could be somewhere here, this is at time t, and then at some future time later t plus Tij, if this particle were to collide, you will see that the distance between these particle I and j should be equal to sigma, which sigma is nothing but the diameter of this particle. So we write that Rij at t plus Tij should be equal to sigma. So now from t to t plus Tij, each of these particles would have moved at a constant speed, because they do not have any force acting on them until they collide, and that is the feature of the hard sphere model. So that means this particle must be travelling at a constant speed of Vi, and this must be travelling at a constant speed of Vj for a time Tij. So then we can write that the separation distance Rij at t plus Tij can be written as the original distance between them, that is Rij, plus the duration times the relative velocity of Vij. Okay, so each of them have a particular Vi and Vj, and then the position at this particular point can be written as the position at time t plus Tij times the relative velocity Vij. This should be equal to sigma. In this expression, we write this Rij is nothing but Ri minus Rj, that is a separation distance vector between I and j, and the relative velocity Vij is written as Vi minus Vj. So now we need this absolute value of this vector. So, and when you try to solve this equation, you will see that this one gives Ri square. So now this is the magnitude of the separation distance, and the sigma square is taken to the left hand side, you get minus sigma square, and then you have this quadratic expressions on t square and then t. Okay, so this basically what we are trying to do here is we are basically taking square of this dot product of the same terms, and then you get this particular expression. So this is the expression that is quadratic in Tij, and then this particular dot product, which is the projection of Rij over Vij, that is the separation distance vector projected on the relative velocity, and that we call it as some factor Bij. Okay, so this equation is now rewritten as v square t square plus 2b Tij plus r square minus sigma square. So this is the equation, and if I solve this equation, I will get what is the time Tij at which these two particles I and j will collide. So now let us look at some example here, under what condition they will undergo collision and when they do not. So to illustrate this example, I have taken a simple 1D problem. Let us say this particle I is at x equal to 0 and it has a velocity of v equal to 0. That means one particle is fixed at some origin. And then there is another particle j, which is at time t is at a distance of minus a. So, a is some number here, it is in the negative direction of the x axis, and then it is moving constant velocity of v naught in the positive x direction. So, that means from this physical picture you will see that after some time t, this particle j will collide with I. In this case the collision is going to occur. So, then we can apply our formula. First we find what is the Rij and at this particular time t, and that is going to be 0 minus of minus a. So, basically the relative vector Rij is basically simply a, and it is shown as the blue arrow here. It is going in the positive direction with a value of a. And then similarly we can calculate what is the relative velocity Vij. So, the ith particle's velocity is 0 minus the jth particle's velocity is in the positive x direction moving at a speed of v naught. So, this Vij is given as minus v naught. So, if I show this as a vector, so the Vij is in the negative x direction. So, the Rij moves in the positive x direction and Vij moves in the negative x direction. Now, the quantity Bij, which I defined as the dot product of Rij and Vij, is negative in this case. So, whenever this Bij is negative value, then the collision is possible. So, this is one result. So, these particles will collide at some particular time in the future. Now, let us take another example where I reverse the direction of the velocity of the jth particle. So, ith particle is as before, it is positioned at x equal to 0 and it is stationary. Now, the other particle j is at the same distance before, like minus a, that is in the negative x axis direction, but then it has a velocity moving in the opposite direction. That means it is moving away from this particle because v is minus v naught. So, it goes in this particular direction, and in this particular configuration you will see that these particle I and j will never collide. So, that means if I calculate Rij for this particular example, you see that Rij remains the same like before in the positive x direction, whereas the Vij, the relative velocity Vij, has changed the direction in the positive x direction as well, because it is 0 minus of v naught. So, it is simply v naught. So, the Vij vector shown as green arrow here and Rij vector, they both actually point to the same direction. That means if I take the dot product of this Vij and Rij, this Bij quantity is going to be a positive number. It is going to be more than 0. So, this gives us a condition that when collision will occur and when will not collision occur. This is because when you have a system of n particle, it is not necessary all the partners will have a collision time. They may be going in the opposite directions and they may never collide also. So, it is important to look at only pairs which would collide at some point of the time in the future. So, one of the way we can screen them is to look at whether this value b is negative or not. And you have to also we have to also remember that not only that the Bij is going to be negative, but also because this is a quadratic equation I said before, the quadratic equation that gives the collision time should be a real value, it can't be a complex number. So, that gives an additional condition that this b square minus v square times r square minus sigma square should also be a positive number. That is because if you solve this quadratic equation, you get this term within the square root, and this number has to be a positive number. That is one condition, and the second condition is this b should be negative. So, once you have these conditions satisfied for a given pair I and j, then you can solve for the time by this solving this quadratic equation, and there is going to be two roots, and then we take the smallest root because it is about time at which the collision happens, and we want to look at the shortest time at which this collision happens. So, this is pictorially shown here. So, this is particle 1, this particle 2. This 2 time scale that you are talking about here can be shown in this particular figure. So, when this particle moves to this, that is the time which is given by the shortest collision times. The other collision time, which is the biggest root, will be the time corresponding to this place. Okay. But then by the time the particle comes here, it has to go through this. So, this is not physically possible. So, we take the shortest time, collision time of the particle I and j. So, this method can be now applied for all the pairs I and j, and then we can get the collision time for each of those pair whenever they can satisfy these two conditions. So, this is actually shown in this particular pseudo algorithm. So, first what we do is we first initiate an array going from I is equal to 1 to n, that is for each particle. We define a variable called time, which is nothing but Tij, and we say that is equal to some very large number. This time big is something like 10 power 10, very large number, so that all pairs, all particle will have certain collision times, but this is not something physical because it has to be kept at a very large numbers. And then now we are going to search for pairs with a finite collision times. So, now you can see that there is going to be a double loop. This double loop is very similar to the way we do force calculation in the soft sphere model, where we find the Rxij, Ryij. So, these are all nothing but Rxij is nothing but Rxi minus Rxj, and this is Ryij, which is Ryi minus Ryj, and similarly this is basically the vectorial component of the interparticle distance vector. And then we apply this minimum image convention, so that we find the nearest neighbor image, and then we also calculate the velocities, that is Vijx, Vijy and Vijz. So, all that is obtained here, and then we calculate this parameter Bij, which is nothing but the dot product of Rij times dot Vij. Okay. So, this is done for one particular pair Inj within this loop. So, then we check whether this Bij is negative or not. If so, then we look at the second condition, that is whether this the term within the square root of the quadratic equation, whether it is positive or not. So, that is given as this variable DISCR. This is given as b square minus b square times Rij square minus sigma square. So, this is sigma square, and this Rij square is basically obtained by squaring the Rij, Rxij, Ryij and then Rzij. So, we are able to get this quantity, and then we check whether this number is greater than 0 or not. So, only when these two conditions are satisfied, then we go to calculate the collision time Tij for the pair Inj using the smallest root. This equation that you see here is nothing but this equation. So, then what we are going to do is, now we are going to check whether the collision time of Ij pair is less than collision time, which is initially put as some very large number. So, this now is going to be updated continuously. So, if that is the case, then we reassign the collision time of the ith particle as the newly found collision time, and then the collision partner of I is going to be j. Okay. So, not only we store the collision time of each particle, but also who are the partners of those collision partners also. So, that is stored here, and then after that we also update the collision partners and collision time for the jth particle in the same loop as well. Again we check whether Tij is less than collision time of the jth particle, and if this is the case, then we update the collision time for j is same as collision time of I, and that is given as Tij, and then the collision partner of j is going to be collision partner of j is going to be I. So, in this particular loop we are basically storing collision time and collision partner of I and j mutually, and this we have to do because initially suppose if I say I is equal to 1 and j may be equal to 2, but in the next cycle the third particle might have a shorter time scale of collision, so then it will be updated accordingly. So, when you come out of this particular loop, what you will see is that you will see two arrays, that is this collision time for each particle and then the partner of each particle's colliding partner as well, and that is something we can get it from this particular looping. And the next step is to find the next collision event. So, the next collision event is nothing but any pair which will have the least collision time. So, now we have looped over all the particle I and j pairs, and then we have found the collision times. So, now we have to sort them out and then find out which partners or which pair of particles have the least collision times. So, to do that you actually loop over particle 1 to n, and then you start with some Tij, some big number, and then you keep looking at for every particle k going from 1 to n, you check whether the collision time of the kth particle is less than Tij or not. If so, then you set that collision time is given by the collision time of the kth particle, and then you obtain also you also store the particle which has the least collision time k into some variable I, and then when you loop over this continuously, what will happen is you will be able to find the Tij which has the least value and the corresponding I molecule also. And then once you come out of the loop, you can go and find who is the partner of I, and that will be J. So, by doing this loop, what we are doing is we are getting the minimum value of collision time in the entire pair of collision times. We basically get the least value of Tij, and we also know the identity of Inj, the particle identity of Inj also is known. So, next step would be to update the particle positions up to time Tij. So, again we do one more loop from 1 to n, and then you can see that the collision time of each particle is now subtracted by the Tij. So, remember this Tij is the next collision time, which we just now found in the previous loop. So, when k becomes equal to I and when k becomes equal to j, then this number will be equal to 0, because the collision time and the minimum Tij are the same. But for all the other particle, the collision time will be always larger than this minimum time. So, we basically subtract the collision time of all the pairs, and then once we do that, then we update the particle positions of kth particle here, current time, current position plus the respective velocity times Tij. So, this is basically updating time the position t plus Tij as the position at t plus v at the time t times the Tij, because this is a force free motion at a constant velocity from time t to t plus Tij. For all this particle it is done, and then you can also apply the periodic boundary conditions, because by updating the particle position, some particle might actually move out of the box, and we basically put them back into the box. So, this allows us to update the particle positions. Only this Inj would have come next to each other. So, they would be just touching now. When you apply this algorithm, the pair Inj would come just to a touching distance, whereas all the other particle would have moved to some distance respect to their particular velocities and positions. Okay. So, this could be some particle m, this is particle n, this particle p. So, all these different particles would be moving to a different distances with respect to this particular algorithm, whereas Inj alone would have moved such a way that they would have actually just touching each other, because we have found the minimum time, minimum collision time and the respective partners. So, in this case it could be some Inj, and when you apply this, the collision time of Inj would be equal to 0, and then if you look at Rx, Ry, Rz of those Inj, they would correspond to just a touching position. That is the time, the moment at which the collision will happen. At this particular point, now what we have to do is we have to think about updating. So, when a physical collision happens, there is the exchange of momentum, and the energy has to be conserved, because there is only kinetic energy in this particular system. So, therefore, we have to update the velocities of the colliding partners also. So, the idea to do that would be we have to enforce the conservation of kinetic energy and linear momentum. So, the way you do that is basically the ith particle's velocity after collision is given as the velocity before they collide plus some delta change in the velocity Vi. Similarly, for the particle Vj, after collision value would be equal to the before collision value minus the small change in the velocity of Vi. And this particular small change here is actually obtained by ensuring momentum conservation and kinetic energy conservation, and it can be shown that this is given as minus B by sigma square times Rij. And this particular algorithm is actually shown in this particular example. So, you can think about this is particle j, this is particle I, Rij vector is in this particular direction. And then if you look at Vi and Vj, you can think of that initially this particle Vi is actually moving in this particular direction, this is Vi, and this particle j is moving in this particular direction, and then this Vij is basically the Vi minus Vj, that is given as this particular value. So, now this change in the velocity of ith particle is along the direction of Rij. So, that is what is shown here, this delta Vij is along the direction of Rij vector. Okay. So, what we are going to do is we are going to add this delta Vij to Vi. So, when you add Vi plus delta Vij, this is going to be the new velocity of the ith particle, whereas for the jth particle this is the old velocity, and then we subtract minus delta Vi. So, the minus delta Vi is in this particular direction, and then when you add these two you get the new velocity for j. So, now this algorithm says how to obtain the change in the velocities for ith particle and how the velocities of I and j should be updated. So, when we do this, we ensure the velocity of all the other particles other than the colliding particles, they remain unchanged because they do not participate in this collision. So, only the colliding partners would have changed their velocities so as to conserve kinetic energy and momentum. So, after the position and velocity of the colliding partners are updated, then we can actually go back and recalculate. Again, we go back to the first step where we again sum over all the pairs, find out the collision times and collision partners. Then you go to the next colliding partners, and then you update the algorithm. So, you can see that what we have just done is for carrying out one particular collision, and then we do many such collisions over a period of time, and this is analogous to integrating equation of motion in time. So, in a soft sphere model, our idea is there to take time step, very small time step, and each of those time step you calculate forces, and then you update velocities and positions, and then you move in time slowly step by step. Whereas in hard sphere model, what we are trying to do is that we are looking at collision events. So, one after the other collision events we execute. Between those collision times we update positions and velocities, because there is nothing happening between the collisions, particles are moving at constant velocity. So, it is very easy to update particle positions and velocity during those times. So, we have to only worry about what is the next colliding partner and update the and ensure the conservation laws such as linear momentum and kinetic energy. And this can be repeated over many number of simulations. That is why when we talk about MD simulation of soft sphere model, we say so many MD steps have been done, or the simulation was carried out for so much time. Whereas in MD simulation of hard sphere, we say the simulation is carried out for 10,000 collisions or 1,000,000 collisions. So, here the number of collision or the collision events is basically surrogate for the time scale in this particular problem. Now, this algorithm what we discussed is focused on hard sphere system, but this method can be generalized for other discontinuous potentials such as square wave model, where you can see that there is a discontinuity at r is equal to sigma 2 as well as at r is equal to sigma 1. So, what we have done so far is only the collision occurring at this particular location, but there is also collision going to happen in this particular location in the case of square wave model. So, there are MD algorithms which will take care of such two-point collisions as well. And then there are other models known as this hard sphere with Coulombic interactions. For example, you might have particles which are hard, but then they can also have charges. So, the potential for such a particle would have a combination of hard and soft potential. For example, it might look something like this. So, this is the continuous part which is coming from Coulombic interactions. But at the time they touch each other, then it goes to infinity. So, you may have a combination of the soft and hard. So, up to r is equal to sigma, the potential is infinite, but once you go beyond r is equal to sigma, it forms a very nicely decaying u proportional to 1 by r, which is easy to differentiate. Okay. So we have to be careful when you have such a combination of hard sphere and soft sphere combinations. And then not only spherical particles, you can also think about hard non-spherical objects, something like the spherocylinder or ellipsoids, which has an elongated shape or maybe a disc like shape. Okay. So when you want to look at a hard particle simulation of non-spherical shape, similar algorithm can be extended. And you will see in the literature there are MD simulation with the dumbbell kind of diatoms, where two atoms are connected by a rigid bond, and they are also this beads are also rigid. They are basically two hard spheres connected by a rigid rod, or you can be simple hard lines without any finite size to the beads. So there are many simulations of this similar kind, and you will see that the algorithm for simulating such discontinuous potential is very similar to how we solve the MD simulation of hard sphere systems. So we are taking only one example of hard sphere system, but for more specific cases like this, the algorithm can be extended to incorporate these additional potential also.
So actually topics are a bit difficult, but when we go back and see the lecture again, then we're able to connect and find out, yes, okay, this is happening right now. Reading for the first time seems little difficult.
Okay. I mean, is it something like, would it help if I go a little slower, or
the speed is okay. There's nothing wrong with the speed.
So the material itself is a little hard, is it?
Sorry?
The material itself is a little hard, is what you're saying.
Yeah, but for me, personally, I'm just reading it for the first time. So.
Okay. Yeah. Thanks. Yeah.
Sir, in the velocity update, we are calculating the velocities after collision. Sir, in that for I and J, the change in velocity we are giving, why we are reducing the change for J particle?
I mean, it's not like we are reducing. It can be any sign, because you see this delta ij here. Yeah. So so what you can do is to see this principle, what you can do is you can take a one-dimensional model. You take a particle I and particle j, and with the mass m and the velocity vi and vj, and then if you look at the conservation of momentum and kinetic energy, you will see that after collision the vi prime will be equal to vj, and vj prime will be equal to vi. That is, for one dimensional system, what happens is that the particle will just exchange their momentum as long as they are of same size and same mass. Okay. So this this particular principle is now actually extended for a three-dimensional collision, and that's what we are trying to see. What is the net change in the velocities of the I and j, and that comes out to be this particular expression. Okay. So I didn't show, I mean, you can actually show this particular expression, derivation of this, but I thought I'll skip it because it involves a detailed calculation of this. So it doesn't, it's not that I'm just adding and subtracting here. This delta vi could be plus or minus itself, right? So yeah. And then from here itself we can see, when I add this, okay, when I add this two terms, you can see the momentum before and after is conserved, that you can readily see from here. But what is not apparent is the conservation of kinetic energy, but then after applying this, you can show that kinetic energy is also conserved. That is actually implicitly mentioned in here, because the way we calculate delta vi is basically enforcing simultaneously conserving kinetic energy and linear momentum.
So these equations VA after is equal to VA before plus delta plus or minus delta VI, these you derived from linear momentum or combination of kinetic energy and linear momentum conservation?
Combination of both.
Yeah, I mean, this looks like, like direct linear momentum conservation M1 V1 like that.
Yeah. So that's what I'm saying. So it's very easy to show for a one-dimensional system. What you will show is, you will show that M1 V1 plus M2 V2 is equal to M1 V1 dash plus M2 V2 dash. This is the conservation of linear momentum, right?
Yes, sir.
And then we can also write similarly half m1 v1 square plus half m2 v2 square should be equal to half m1 v1 prime square plus half m2 v2 dash square. So now we got two equations, and then you can solve for, and then if you solve these two set of equations, you should be able to show this. That is, v1 prime will be equal to vj, v2, I'll just replace this. The solution of these two set of equation will tell you this. Okay, so after collision basically the particles would have exchanged their velocities, and now this is done for a single one dimensional system, and then what I have shown here vectorially is the generalization for a 3-dimensional system.
So one more thing, in last class we derived based on constants, no sir. So if we apply constants here also, so velocity, these can also change, no sir. Constants.
Those things are applied for, again remember, for soft sphere models where the force was obtained from a continuous potential, right?
Okay.
Here we are talking about totally different. That's what I was saying in the beginning. The way we do simulation of MD simulation depends on whether we have a soft sphere model or a hard sphere model. Okay, so in the soft sphere model, our approach is to get forces by taking derivatives of the potential energy, because the potential energy is the continuous function of r. So the derivatives are possible, force is possible. Then you can get the acceleration that can be substituted in a time step manner to update positions. The same approach cannot be used in MD simulation of hard sphere, because there is no force acting between collisions. Forces are acting only during the collisions. Okay, between two collisions the particles are moving at a constant velocity because there is no force acting between those collisions, right? Because the potential, as you can see here, is felt only when there is a collision and none otherwise. So it will be waste of time taking small time step and then updating the particle positions and velocity, because particles are moving at a constant velocity anyway. Whereas in this case, for every delta t, the particle velocities are changing, and that is why we do in a time step manner. Here collisions only matters. Between collisions the particles are moving at a constant velocity, so it is easy to update the particle positions and velocities like I showed here. So in this particular example you can see the particle position over a time of Tij is updated by this particular algorithm, r of t plus v of t times Tit, because this v is constant over a period of Tij, and this is not the case in the case of a soft sphere model. So that is a key difference that you have to understand. You follow?
Yeah, yes sir. Okay sir.
So a general question from the last assignment. When we calculate the density from the radial distribution plot, we should consider the area under the total curve or to the only certain sigma?
So what was the question?
Finding density from the radial distribution plot.
Okay, so which assignment you are talking about?
Last assignment.
The fourth one.
Third one maybe.
Oh, okay. But there is no question asking you to calculate the density, right?
No, sorry sir, not the density, it's the number of nearest neighbors.
Yeah. So nearest neighbor is a different thing. So for nearest neighbor, all you need to do is you have to integrate the g of r until the first minima occurs. So remember we talked about the meaning of radial distribution functions, and then you get a first peak for the nearest neighbor, second peak for the second nearest neighbor, third peak for the third nearest neighbor. So I think you are talking about the second question where it said find the nearest neighbor distance and the number of nearest neighbors.
Yes sir.
Yeah, so that basically means finding out the location of the minimum, the first minimum in GFR, and then integrating GFR up to that particular position to get the mean number of neighbors. You can actually take a look at the discussion that we had about the structural quantities, right? And
Okay.
And then you can see that how we defined, especially I showed an example of nitrogen, liquid nitrogen, water,
Yes, sir.
I showed how to find the nearest neighbor, right? So it's basically direct application of that. So
Actually, I just want to know how to find the density using radial distribution, sir. Number density or
okay, so basically if you're looking at density, so if you you're talking about some local density.
yes, sir.
Okay, so all you need to do is take G of R and multiply by the average density. That will give you the local density at any given distance R, right?
Okay, sir.
Yeah, this I think also was discussed in the class. Yeah,
So, but what shall we
go back to that go back to that discussion on structural quantities, lecture 9. You can see that pictorially we have discussed what is the meaning of G of R and how to get the average number of neighbors on all that.
Thank you.
Yeah.
So I was asking about what shall we substitute for G of R, because the formula says it is n equals to 4 pi rho in integral and then G of R into R squared dr.
Again, are you referring to the assignment problem or are you referring to the lecture?
Yes, sir. Yes, sir. The same problem. We know the limits that what is the lower limit and the upper limit. But what shall we substitute for the R value?
What we substitute for the value of?
G of R.
I thought the G of R is given in the plot, right? Isn't G of R given in the plot?
I don't think so. It was given.
Yeah, it is there. I'm just checking.
Okay.
So G of R is actually given. Okay, let me just share this. You're talking about the second problem, right?
Yeah.
So you can see that G. Okay, what did I do? Yeah. So G of R is actually given here, and then you have to integrate between from something like 3 point maybe 1 or something to up to some 5 point something. The area under the curve.
Okay.
Yeah, the area under the curve. So this is something you have to do with some numerical technique. Take some trapezoidal rule or some Simpson rule or one of those rules, and then you integrate this curve.
Okay.
Yeah?
All right.
Yeah.
Thank you, sir.
Yeah. N here is basically the integral of G of R square dr over a distance of some value which was I think from 3.1 to 5 point something, and then you also would need a density, and I did not give a density in this in this particular problem, but I was hoping that you will find this out by looking at so if you look at this example, I given it's an LJ fluid and then the temperature is also given. Okay, so you should be able to probably find out what is the corresponding density would be. Okay, or you can choose a particular density and then find that number also.
How to get that functional form from that RDF plot?
So functional form you will not get it, you have to do some numerical integration.
Oh, okay.
Yeah, otherwise what you can basically, you read these points, right? You read these points and then well, you don't have to read this point, because all you need to do is that you have to integrate G of R square, right? So you pick up some R points along the curve and then you can take square of that and then the value of G of R those places, and then do some numerical integration like Simpson rule or trapezoidal rule, and then numerically do that. Okay, by the way, all of you are familiar with some numerical techniques like simple numerical integrations, right? I mean, you might have done in some math course. I assume that you know.
Yes.
Yeah.
Yes, sir.
Okay, good. Or you can just look it up any any book on numerical methods. Trapezoidal rule and Simpson rules are very easy to do. You can just do it in Excel.